Welcome, everyone. Thank you for joining us for today's keynote presentation, Fully Automated IHC Multiplexing, Techniques and Assay Development, presented by Dr. Mark Hellewell, Discovery Reagent and Training Lead, Companion Diagnostics and Discovery, Roche Tissue Diagnostics. My name is Xavier Gutierrez, and I will be your moderator for today's event. We are delighted to bring you this educational web seminar presented by Labroots and sponsored by Roche Diagnostics. For more information about our sponsor, please visit www.diagnostics.roche.com. Now, before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want during the presentation. Simply click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box. Our speaker will respond to your questions via email following the presentation. If you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're experiencing a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Now, without further ado, please join me in welcoming Dr. Hellewell. I will now turn the presentation over to him.
So we're going to begin with some background and utility for multiplexing. Within the research market for tissue diagnostics, this has been one of the fastest growing and most popular areas of interest within research. And that's down to the fact that you can basically perform multiple detection of markers on the same section of tissue. And this is particularly useful for research because in most cases we're dealing with precious samples. We're looking at panel developments and multiple markers relating to the particular disease area or the companion diagnostic development, which may be researched. We can also look at colocalization and interaction in terms of how those proteins are being expressed and how they're interacting with each cell in terms of the tissue itself. Also, in relation to this, we can look at cell population studies, particularly looking at expression patterns and also looking at the organization of the tumor. All of this leading towards an increased diagnostic and predictive accuracy. At the moment, a lot of the multiplexing work we're seeing is being performed within the research sector, but we hope within the next few years, we will see this moving forward towards the clinical space. And in turn, increasing medical value for clinical diagnostics. So in terms of multiplexing, there's two different key methods for IHC multiplexing, and that's using fluorescence or chromogenic detection. Historically, fluorescence has been the method of choice because it's easy to see where there is colocalization of markers, basically where two different fluorescent markers overlap, it creates a second color. In the past, for chromogens, with traditional chromogens such as DAB and red, when these do colocalize, it's very difficult to see where these colocalization events are occurring. However, with the introduction of our new chromogens, which have translucent properties, we can see color changes. So these chromogens act just like fluorophores, and when they do overlap, it creates a new color, which is a great benefit for people that don't have fluorescent equipment to be able to detect these particular markers. One of the big advantages for multiplexing as well is automation. We have automated platforms which take away the complexity of the multiplexing assay. Within this slide, you can see in the top right-hand corner is a manual workflow diagram which shows all the touch points which would have to take place to create a manual IHC assay with multiplexing. However, with automation, we take away a lot of those touch points and provide full standardization, reduce bench time, and also with the introduction of ready-to-use products, we can ensure that we get a high level of reproducibility across any assays which are developed. So with chromogenic multiplexing, which is the area we're going to focus on primarily, It's really expanded over the past 2 to 3 years with the introduction of these new chromogens and the expansion of the automation that we can offer within Roche Tissue Diagnostics. So at the moment, we're seeing 5, 6 different markers on the same slide. And here we've just got a few examples of what we can offer in terms of fully automated and ready to use multiplexing detection. And as I mentioned earlier, this is all down to how the new chromogens work. Conventional chromogens such as fast red and fast blue have a very broad absorbance spectra. And this means they're very difficult to deconvolute. And if they overlap, it's very difficult to see different colors emerging. If we lay over additional chromogens and counterstains, such as hematoxylin, DAB, and silver, you can see there's such a broad array of spectra there that it's going to be very difficult to see colocalization events. The new discovery chromogens that we've created are very much based around a HP inkjet printer, where you would have 3 different color cartridges which are able to create any particular color you like by overlapping. And you can see here that each of the discovery chromogens, discovery yellow, purple, and teal, all have very narrow absorbance spectra. So when they do overlap, it's very easy to see where these colocalization events take place, and also very easy to deconvolute using image analysis tools. So with our translucent chromogens, as I mentioned, we do show the same properties of fluorescence. So basically where colocalization takes place, we can see a new color emerging. So here we've got 2 examples of the colocalization staining, where we have discovery purple and discovery yellow. And when they colocalize as a dual stain, it creates this new color, which is a dark red or an orange color. So you can see where those colocalization events are gonna happen. Another example here is where we've got teal for CD163 and yellow for CD68. And when they colocalize, it creates the green color, which you can see in this image. The same 2 markers, CD163, CD68 in purple and teal, and when these colocalize, we get this dark blue or indigo color showing where the colocalization events take place. And obviously the huge benefit here is that you don't need any specialist filters, you don't need a fluorescent scope. All of this can be visualized under a brightfield microscope. So let's talk a little bit about method and assay development for multiplexing. Multiplexing is a complex area. There's no rule book in terms of how these assays are created, but with our experience with the research, tissue research market that we've been working in, we've put together this presentation which will give you some outlines as to how to create your multiplex assays. So let's look at some of the methods of detection. So this first method here we're going to talk about is an antispecies approach, where we deposit our fluorophores or our chromogens with an enzyme. So the big advantage here is there isn't really any species limitations. The way in which the enzymatic deposition occurs allows us to have an increased signal intensity, greater stability, and much easier to transfer between a fluorescence and a brightfield procedure. Downsides here can be that the assays do take a little bit longer, and if you are using certain fluors, they can be bleached, or they can be susceptible to any denaturing or quench steps. And this can happen by H2O2, which is quite commonly used within these types of assays. These are a couple of the detection methods that we have available for the discovery. So this is an antispecies or anti-hapten approach with enzyme deposited chromogens. On the left-hand side, we have the multimer detection, which basically is an anti-species secondary antibody, and conjugated to that is your enzyme which is going to drive the chromogenic reaction. And in this case, it can be either HRP or AP. And on the right-hand side, we have a hapten detection method. And here what we use is a proprietary product created at Roche Tissue Diagnostics, whereby we conjugate a hapten, or a synthetic label, to a secondary antibody. So in this case, we use HQ or NP. And then we come in with an antibody directed against these synthetic labels. So we come in with an anti-HQ HRP or an anti-NP AP. With this, we really see a huge increase in specificity, sensitivity, and signal intensity. And we can use this method with chromogens or fluorophores. And these are excellent for detecting low-expressing targets. So once we've decided on the type of detection method that we're going to implement, we recommend not diving straight into a multiplex assay. What we advise is optimizing each antibody individually. So once you've decided on the panel that you're creating, optimize each of those individually, work out which marker is going to work best with each detection type, with each chromogen type, and then create your staining reference library. So you've always got something to go back to in order to determine if that stain is working effectively. If you were to dive straight into a 4 or 5-plex assay, it's very difficult to work out what may or may not have gone wrong with the assay if there are problems at the end of the staining run. By having that reference library, you can go back and ensure that everything is working effectively in each of the different detection methods. One of the biggest issues we find with multiplexing assays is actually creating an assay where the different markers are able to be configured with their different antigen retrieval methods. So in some cases, different markers react differently to different types of antigen retrieval. And it's important that we try and find some common ground. So trying to find a retrieval method which is going to suit all the different antigens within that particular tissue section. With the software that we have available for the discovery, what we can offer is progressive retrieval. And what we mean by that is basically being able to add additional retrieval as we go through the procedure. So you may start off with in your first sequence by staining something which has a very light antigen retrieval. And then towards the end of the sequence, we've added or progressively added more retrieval to hit those additional antigens throughout the sequences. The two main types of retrieval that we use or our customers use would be either a heat retrieval or enzymatic retrieval. And as I mentioned, with heat, try and find a method that's efficient for all the antigens. We can add additional heat applications through each sequences. And then we can also use different types of retrieval buffers. So in terms of a high or a low pH retrieval buffer for each of the different markers. Enzymatic retrieval can be a little bit problematic because it can have a negative effect on other targets within the tissue. So in this case, if you do have to use an enzyme, we always recommend using that in the final sequence. So you're not going to affect any of the other markers within that particular multiplex assay. As I mentioned as well, we offer either sequential or cocktailed multiplexing options. So with the sequential method, what we do is we actually apply each antibody in detection individually. And then we move on to the next sequence. And in between each of these sequences, we perform a denaturing or elution step, which avoids any cross-reactivity by breaking down the initial antibodies which may have been applied. This allows us to use the same species, same enzyme detection. So you may wish, as you can see in this diagram, we can use all mouse primary antibodies, and we can also use all HRP enzymes to drive the chromogenic reactions, just by applying those denaturing steps in between each sequence. With the cocktailed antibodies, you can see here that we can actually apply 2 different species at the same time. And as you can see as well, by applying 2 different enzymes, we can perform up to 4 different markers over 2 sequences by performing this cocktailed method. This can be a little bit problematic because you have to ensure that all your detections are configured correctly, but it can help by reducing some of the runtime. Antibody detection sequence is also key importance. As you can see here, we've got 2 examples of the same stain, but using different types of detection. So it's important to determine the optimal type of detection that you're going to be using. So on the left-hand side, we've got a multimer detection, and on the right-hand side, we've got a hapten-based detection. And you can see the increased sensitivity and specificity of the hapten detection is giving a more optimal signal from that particular stain. So it's important to ensure you're using the best possible detection before you create the multiplex assay. If you plan to use a silver detection as well, it's also important to be conscious that it can be affected by hydrogen peroxide treatment or HRP neutralization. And this should be placed last in the sequence because it can cause fading to that particular silver chromogen. So DAB is a traditional chromogen used in IHC, and it's a great chromogen, but we can see problems when we're actually using it within a multiplex assay. So here we're going to talk about something that we call the umbrella effect of DAB. And DAB, we think, inhibits staining of other markers in close proximity by basically creating a molecular shell. So what you can see here is if we try and stain our marker with DAB, you can see it creates the DAB deposits around that particular marker. And next to it, we have another antibody, which isn't in such close proximity. And we can come in and we can stain that effectively. To the left-hand side of the DAB marker, you can see a third, and the molecular shell that we say with the DAB can actually prevent that particular marker coming in to bind effectively. With the staining images on this picture as well, what you can see is that just by alternating the position of the DAB stain, we can actually improve the quality of the staining. So on the left-hand side, we've used DAB as the first marker for CD20, and it's very difficult here to see the CD30 in silver. And just by swapping these over and putting CD30 first and CD20 second, you can see that the staining is much more apparent. And just these changes in sequence can have a big impact on chromogenic multiplexing. So here we really need to consider marker localization. Ideally, and this isn't always going to happen, it would be optimal to consider markers that don't overlap. This is quite difficult in most cases. So if you do need to choose markers that are going to overlap, it's important to choose the correct chromogens that you may wish to use. So here we can see by using Ki67 in yellow and CD20 with purple, it's very easy to see where the colocalization takes place. However, below where we have CD8 in purple, CD3 in silver, it's very difficult. We just get almost a black stain, and it's very difficult to see where those 2 different markers are. So here we have an example of this chromogen sequence and changing these to actually create the best staining outcome at the end of the sequence. So here we have CD8, CD3, and what we recommend doing is actually creating 4 different slides with different combinations of, firstly, the primary antibody, and then secondly, the detection. So we start off with CD3, CD8, and then in the second set of slides, we swap over the primaries and we use CD8 followed by CD3. And you can see here, just by swapping the order of the detection and the primary antibody, it really has a big impact on the type of staining that you would see, with the 2 images on the left being more optimal because you can see the purple and you can also see the DAB staining. So one of the key rules of thumb that we have seen is we would suggest always staining the low expressor first to give the best possible staining. I touched on this briefly earlier, so denaturation and neutralization. And these are methods to prevent cross-reactivity within a sequential multiplex staining. So an example would be if you're using two mouse primary antibodies, if you didn't perform denaturation, this is what would happen. What would happen is you would come in with your first primary antibody, your secondary, and then your chromogen. Without denaturation, you would start on your second sequence. You'd come in with another mouse primary antibody. You'd come in with another anti-mouse secondary antibody. And the problem here would be that without denaturation, that secondary antibody would actually bind to the previously bound primary antibody, creating cross-reactivity within the stain, as you can see here. Neutralization is a way of deactivating HRP enzymes which would be conjugated to your secondary antibody. So if we weren't to perform neutralization, we would come in with the primary, secondary, conjugated to HRP. We would perform the chromogenic reaction. And then in the second sequence, we would do the same again. We would come in with the primary, the secondary. Because this is also conjugated to HRP, any remaining HRP from the previously bound complex can actually create cross-reactivity within the stain. So we would see both DAB and purple staining non-specifically at potentially different sites within the tissue. So how do we go about performing denaturation and neutralization? So we've got three different methods that we advise the use of. Firstly, heat denaturation, which can be used when it's the same primary antibody species, and also when it's the same enzyme species as well. With the same enzyme type, what we found is by performing a low pH, high SDS buffer, such as Ultra CT2, at a high heat, this actually deactivates both the immunoglobulin complexes and also the enzyme that you're actually using within that particular assay. We can also use acid denaturation. So by using a very low pH solution, such as Discovery Antibody Denaturing Reagent, this can help deactivate and neutralize any previously bound primary antibodies within the sequence. If you're looking just to perform HRP neutralization without any denaturation, then you can also use discovery inhibitor or hydrogen peroxide to deactivate the HRP conjugates previously bound. When we do perform denaturation, this is what happens. We come in with the primary, the secondary, and the chromogen. We apply a high heat and Ultra CC2, so that's the low pH, high SDS buffer. And what this does is it's going to break down those previously bound immunoglobulins, such as the primary and the secondary antibody. Meaning when we come in with our next sequence, we have our primary, our secondary, and this secondary is only going to bind to the primary because it has nothing else to bind to. So this means we're going to get two discrete signals without any cross-reactivity. With neutralization, again, we come in with our primary, our HRP conjugated secondary, we apply our chromogen, and then we apply H2O2 or discovery inhibitor. And this is going to deactivate any remaining HRPs within the tissue. So that when we come in with our second primary antibody, our secondary conjugated to HRP, again, we're just going to be left with two discrete signals. So with the denaturing or elution methods that we can offer, as I mentioned before, we tend to recommend the use of a high heat and a low pH buffer to perform this type of denaturation. But you can do this in different ways. So we have a chemical elution using the antibody denaturing reagent, which is a very acidic solution, which is pretty useful for when you're using maybe a low order multiplex. But by applying acid continually to a high order multiplex, this can start to interfere with morphology across the tissue. The second image is using reaction buffer or a TBS buffer with high heat. And you can see this also is effective, but by performing a combination of acid and heat, you can see that the actual staining can start to deteriorate because the antigenicity starts to be affected by the different types of elution methods. One way to check your denaturation efficiency is to run dropout controls. And this basically means by removing a component of the assay, we can actually check to see whether the denaturing is working. So on your test protocol, you can see we've got two targets and we're staining with a anti-mouse secondary and also an anti-mouse secondary within the second sequence. So here, by performing a dropout control on the second protocol, by taking away the two chromogens, or taking away the first chromogen and then the second primary, if we see no cross-reactivity, we should see no staining. If we see any staining at all, then that's telling us that cross-reactivity is taking place, because we shouldn't be able to see any cross-reactivity if the denaturation has been effective. Okay, so let's move on to actually how to create a protocol. And throughout all of these methods, we always assume that we've started with a single stain and we've created a staining reference. So we'll start off with a 3-plex assay, where we need to consider pre-treatment, antibody species, marker localization, and the detection types that we're going to be using. So the tissue here that we're going to use is lung, and we're going to be running it with TTF1, synaptophysin, and CD56, with DAB, purple, and yellow. And based on the single staining references that we've created, we've decided that we're going to run TTF1 with DAB, which is nuclear, synaptophysin, which is cytoplasmic with yellow, and CD56 staining the membrane with purple. And here we've given you two examples of optimal and non-optimal staining. So on the left-hand side is what we think is a good quality stain. We started off with nuclear staining with DAB, followed by the cytoplasmic staining in yellow, and then finally the CD56 with purple. On the right-hand side is non-optimal, and what we've done here is actually to swap around the sequence just to show you what would happen if we were to run DAB last in the sequence. And what you can see here is that DAB has almost masked everything else within that particular stain. So it's really important to be sure where you're going to be using your DAB. And in this case, DAB is excellent for nuclear staining for some of the lower expressing markers within a multiplex. So the next one we'll look at is a Fourplex assay. In this one, we have a lymph node and we're staining it with CD30, CD20, CD4, CD8. And we're going to be using DAB, purple, teal, and silver. And again, we've assumed that we've optimized using our single stain references. And therefore, we've created the following initial stain, which is CD30 in silver, CD4 in teal, CD8 in purple, and CD20 in DAB. And what we've done here is actually we've created an expression ratio. And as I mentioned before, we always recommend running the lower expressing marker first, so CD30. CD4 and CD8 should be equivocal in terms of expression ratio. And then CD20 is going to be the high expressor. And here we've created an example where we've actually used DAB as the high expressor, which isn't always advisable, as you can see from the staining image. And what you can see here is the CD20 is almost masking every other color within that tissue section. You can see a little bit of the teal, but it's really difficult to see the purple or the silver coming through within that particular stain. So what we're going to do here is actually move the CD20 further down the sequence, whereby CD30 it remains in first position, CD20 in second position. And you can see immediately, just by changing the order of that sequence, some of the other markers now become apparent. So ideally, within this particular example, we probably wouldn't use DAB as our chromogen of choice, just purely because of the number of markers that we're trying to detect and the way in which DAB can mask other markers. But we're just using this as an example for you to see where we actually can move around the different sequences, and this will actually create a more improved stain and visualization method. Another example here is the use of red and purple. And what we found is that red actually gets more pink in terms of its hue if you use it in later steps within the sequence. So on the top left image, we've used CD8 with purple, CD68 red, Ki67 in yellow, and then a pankeratin with teal. And you can see that the red staining is very dark for the CD68. However, if we on the right-hand side move CD68 to the last part of the sequence, the hue has changed completely and is actually looking a little bit more like the purple. So it's very difficult to actually notice the contrast between the two different markers. So it's important to consider where you're actually going to be using these different chromogens within the sequence. Another example here, where we're using colocalized antigens of CD30 and CD20. The top left is the optimal staining, where we've used CD30 first, CD20, CD8, and then Ki67 in teal. And you can see that by moving the different sequences around, it actually really changes the way in which the staining works. So the top right staining example here, we've put CD20 first, and it masks everything. The bottom left, we've put CD30 towards the end, and it's very difficult to see that staining at all. And then in the bottom right, what we've done is actually to take DAB out completely. And in this case, we're using a newer chromogen, Discovery Green, which we thought may help actually improve the staining sequence. But in this case, it's actually still not optimal. The example here, though, where we have implemented Discovery Green in place of the DAB, has really shown a big improvement in the way in which we can actually visualize these different markers. So the two images to the left, we're using CD20 with DAB. And we can see some of those actual markers there, but it's very difficult to make out each of them discretely. On the right-hand side, actually, what we've done is to take away the DAB and replace it with green. And by doing that, everything becomes a lot more clear. It's much more easy to see those different markers because of the way in which the green chromogen works and allows us to have better contrast against the other markers that we're using. Where we have non-localized antigens, we have a much greater flexibility in terms of the sequence that we're running. In this case, because none of them are co-localized, you can really place the chromogens in any particular order. So here we've put CD68 as in the first position, CD8 in second on the left-hand side, and then on the right-hand side, we've alternated these. And you can see there's not a great deal of difference between the staining patterns. And this is really an important aspect to consider to ensure that the way in which you're looking at these markers and the way in which you're applying the different chromogens to get the best possible staining. So to summarize these detection tips that we've mentioned, this is a recommended chromogen sequence that we've put together. And as you can see, silver really can be inserted anywhere within the sequence, but it's really dependent on the type of neutralization methods you may be using. If you are using H2O2 neutralization, then it's important to use this right at the end of the sequence. Also consider the masking effect of DAB, particularly in colocalized markers, and how DAB could interfere with the staining of these different markers within the tissue. Red, we've found, does get more pink if it's used in later steps within the sequence. And you definitely get a better contrast between the red and purple if it's applied early in the sequence, particularly before yellow and teal. As I mentioned with silver, it's important to use it at the end of the sequence if you are using neutralization. And also teal, we found, does fade a little bit if it's a prolonged exposure to H2O2. So those are a couple of tips to consider. So I also want to touch upon some of the fluorescent options that we have available for the Discovery Ultra as well. Around two and a half years ago, we launched the Discovery Fiveplex immunofluorescence procedure. And with the IF procedure, what this offers is a more robust, pre-optimized procedure whereby the customer can come in with their primary antibodies and just, excuse me, apply these primary antibodies. And we've already preset the detection order and with the neutralization and denaturing steps pre-applied. So this is a lot more easy to use by applying the ready-to-use products that we have available. The customers have pretty much a plug-and-play option available to them to create a fluorescent 5-plex assay. And these are what the HRP Fluorophores that we use look like. All of these are tyramide-driven fluors, and we have rhodamine 6G, DCC, Red 610, FAM, and CY5. One of the big benefits we found with our products and by using the software that we provide is the ability to switch easily between brightfield and fluorescence without the real need to re-optimize. So for example, you could optimize your CD3 or CD8 antibody with DAB. And instead of re-optimizing for fluorescence, you can simply deselect DAB within your protocol and then reselect one of the fluorescent markers, and you will get equivocal staining within your tissue. And then within the 5-plex, you can build upon these options to create up to 5 different markers on the same slide. So here we have FOXP3 with Discovery FAM. We have CD68 in CY5, CD8 with Discovery Red 610, CD3 with DCC, we have CD20 with rhodamine 6G, and that would give you your 5 different markers. And this is created with the 5-plex procedure. What you can also do is actually to utilize the universal procedure within the Discovery Ultra software if you are looking for greater flexibility, if the 5-plex procedure doesn't offer you everything that you require. So in terms of multiplexing, where are we heading? One of the big demands that we're seeing from the clinic and also from pharma is the increased demand on multiplex panels or pre-optimized, fully automated multiplex panels, specifically disease-focused, such as immuno-oncology. And we're also seeing a big pull from the chromogenic side as well as the IF side. Another demand that we're seeing as well is the use of multiple single copy mRNA stains as well. The ability to detect multiple RNA or DNA targets in the same tissue and potentially adding protein targets with that as well is becoming very popular as well. So an example here within the image is a duplex mRNA stain along with a duplex IHC as well. One of the products we're also working on is the ability to detect proximal events within the tissue. So an example here is the ability to see where PD1 and PDL1 is interacting, not co-localizing, but interacting. So when we see a proximal event, so within 40 nanometers, that is when we see staining. If these two markers are not in proximity, then we don't see any staining. And the examples that we have here on the right-hand side is where you can see the PD1, PDL1 interactions in purple. We can see the non-proximal events of the PD1 in yellow. And then we've also stained it with two additional markers as well, CD8 and CD68 with IHC. So this gives a real different type of multiplex assay by providing a high level of information from the particular stain. And also this could be combined with other targets as well, such as mRNA. And finally, in summary, with the increased demand in multiplexing, what we're trying to do for our customers is really increase the number of tools available. What we're seeing is as the demand on the number of markers increases, obviously complexity also increases. So it's really important to choose the best method for your application. In some cases, IF may be the best method. In some cases, brightfield may be the best method. But it's important to look at all your markers individually to actually consider the type, the localization, expression levels, and then alternate detection to determine the best fit. As we saw in some of the examples, it's very important to utilize the ability to use the sequences within the software to create the best possible staining combinations. And as I mentioned earlier as well, there isn't really a rule book at the moment for multiplexing. We've got a lot of experience in this field, and by working closely with our customers, we've tried to give the best possible guidance for creating these types of assays. They're not easy assays, but they can create something which is going to provide a high level of information for research and hopefully within the clinic, and also allow that increased medical value within the future. And I'd like to thank you for your time, and as Xavier mentioned, I'd be happy to answer any questions that come in via email.
Thank you, Dr. Hellewell, for that informative presentation. I would also like to thank our sponsor, Roche Diagnostics, for making today's educational webcast possible. Now, before we go, I want to let everyone know that this webcast will be available for on-demand viewing through May of 2019. And as a final reminder, any questions submitted will be followed up with via email by our speaker. And that's all for now. Thank you for joining us, and we hope to see you next time. Goodbye.